Okay. Okay. Good afternoon. We'll just get started. So today I want to talk about, I work at PayPal. I want to talk about how we build up Hadoop-powered commerce pipelines. Okay. It's not. Uh-oh. Maybe you want to turn this on? Okay, all right. That works. I'm going to focus on a few things. We're going to talk about, obviously, this is Hadoop Summit, so everything we do is related to Hadoop. After the introduction, I'll talk about what is the Hadoop data pipeline we have built that enable, commerce-related work, dealing with data as related to customers and transactions. And the main talk is going to break down into three different pieces. The first piece will focus on what is the data repository we built to host vast quantity of different types of data. Then we're going to talk about different technology we use to process this vast amount of data and what are the different use cases, different tools and technology they support. And lastly, talking about the data service. What I mean by that is more like the serving tier. The serving tier means that how do I expose the end data results, insights, to the user such that people can actually take advantage of the work you do inside of Hadoop or outside of Hadoop. And talk about some of the future works we'll be doing. Okay, just a little bit about myself. I've been working on Hadoop since 2008 and actually was the original folks working with the Hadoop team at Yahoo. And prior to that, I've been doing a lot of relational database work at all the different database vendors. And today I'm most focusing on the core Hadoop capabilities and using that to build a commerce data pipelines. Okay, PayPal. So so let's show our hands. How many of you actually uses PayPal here? Okay, a big chunk of you. Thank you. So you probably know, right? I mean, PayPal started more than 15 years ago as an online payment solution provider. In the last 2 to 3 years, PayPal has expanded dramatically into offline and mobile payments, right? Be able to have this PayPal icon on your phone and be able to pay at different locations. So this is some of the data I pulled from the earnings report at PayPal. This is recent as of end of Q1 2014. We have close to 150 million customers, close to like worldwide. PayPal today operates in these countries, and we support 26 currencies. And just give you a little sense, right? We do more than $50 billion of payment transactions in a single quarter, and close to 1 billion transactions. And that number grows pretty rapidly. Year over year, PayPal has been growing more in excess of 20 to 30%. This is something I learned myself, actually, after working for PayPal, that 1 out of every $6 people spend on online e-commerce, that money goes through the PayPal Money network. So what does this all mean? PayPal's got many, many petabytes of data, and how do we find the right data platform to support all the data needs is a challenge that we need to solve. Okay. So we use this Hadoop for a variety of different use cases. Since PayPal, deals with money, right? Fraud, credit risk is something very big, very used. That's one of the key early adoption drivers for using Hadoop. And also we're focusing on, offer the right customer experience to use. In this talk, I will focus primarily on the very last pieces. How do I take all the transaction data we captured through the front Oracle transactional database and offer insights for merchants, meaning helping merchants understand how they're doing on the PayPal network and where their sales come from geographically and how their sales vary over time. Okay. Since this platform we have built is built entirely on Hadoop, So the next section will talk about what are the key things we have built from this Hadoop platform. Okay, Hadoop is rapidly becoming the new center of gravity in the enterprise data architecture, right? If you go to a different vendors, people start to use the term data hubs or data lakes. But whatever that is, it means Hadoop is a platform that's holding most, if not all of your data. We look at the use cases people do, right? In the early days, Hadoop is nothing more than a batch system that can do the heavy liftings. All your data refining is going through the Hadoop network, Hadoop systems. And over time, people pushing more ad hoc analytics. Now with Hive 13, the Stinger initiative, you also have interactive SQL-based analytics. Then you have machine learnings and data science work being done on Hadoop. Now at the same time, all the Hadoop vendors like Hortonworks and et cetera is adding all the enterprise features. What does that mean for all of us who are Hadoop practitioners? Is Hadoop is very, very quickly becoming the center of gravity for modern data work. So this is a very, very high level overview of how this data architecture will look like. So to the bottom lower right, you have your Oracle database. If you're talking about transactional data, especially you're talking about data that deal with money, most vendors pretty much still run this thing on Oracle or DB2s or other relational database vendors. Then we take the data on Oracle, then we take it to Hadoop, where it becomes the main data repository. It holds all of your data. Then you do your data crunching, data processing there. Post-crunching, then data can be pushed to your traditional data warehouse, such as Teradata data or Oracle or DB2 for your standard data warehousing type of work. But at the same time, we want to take the insight we get from Hadoop and use that insight to power your operation. What I mean operation is to power your business. So it's whether external user-facing, your web application that your end user comes to use, or your internal analytical applications. These applications are being driven by data and insights we generate from Hadoop. So as data start to flow through this Hadoop-based pipeline, today our folks primarily talking about how the data, the red star and the orange star, how they flow through the Hadoop system and then land at the target consumption endpoint. Okay. The first piece I'm going to focus on is called a data repository. Where do we build a place where we hold all of your Hadoop data? So I'm introducing a concept called a Data Central. Data Central is a central data store we built on Hadoop that's going to offer it as a service such that people can do analytics very easily. Okay. First thing, you bring all of your data in a single place called Hadoop. All your data means could be your transactional data, could be your machine data, your clickstream data. And this is a place where storing both real-time data and historical data. In the case of PayPal, right? PayPal's got data for more than a decade, since the early 2000s, right? We want to keep all this data there so that people can do current analytics, the state of the business, and also allow data scientists to look at data going back a few years or even more to look at trends and patterns. Then you also want to organize data, right? If you just land a raw data on Hadoop, not very useful to the end users, right? You want to organize data in such a way that make analytics easy for everyone. This is something we build such that we can reduce data fragmentation. If you go talk to anybody, when I interview data users at PayPal, one of the key things I've heard is that we have such a huge disparate data repository. It could be transactional database in Oracle, could be a data mart in another Oracle data system, some legacy data sitting in Teradata, and there will be other data sources sitting in the ops center, in the customer call centers, right? data spread across the enterprise at many different places. And the vast majority of time for a new data team to work on data, they are spending all their time to bring data from this fragmented landscape into a single location. So we actually took the step to bring this data, unite them in a single location. Right? And at the same time, we want to make sure that the pipeline we build on Hadoop is low latency, right? Raw data to insights where a business user can use to make a decision or do something about it. Last, not the least, right? Traditionally, people do data processing work on relational database or data warehouse, and you know that per gigabyte or even per terabyte, the storage or processing cost on this platform is far more expensive than that you can get from Hadoop. We want to go ahead and push all this data processing to Hadoop. Okay, so the first thing we do is just get all the raw data to Hadoop. We talked about social media data, potentially third-party data that your firm may purchase from an external vendor, your transactional data, the clickstream data you have. Whether it's structured, semi-structured, or unstructured, you bring all the raw data to Hadoop. The pipeline you build has to be reliable, right? If you deal with data, if you cannot guarantee the reliability, integrity of data, not very useful for any business user to use that. And the quality of the data needs to be guaranteed. That means you have this a way to be able to check, how many how many rows of data is at the source, how many rows lands on Hadoop, make sure they actually matches. Low latency. The traditional enterprise, if you're talking about maybe 10 years ago, you built a gigantic data warehouse, and you pull your data from your SAP, Oracle, or whatever enterprise application have. That typically runs at midnight, and the data pipeline takes about 5 hours with any luck. Before people show up at work, before 8 a.m., your data is done, your BI reports, dashboards are completed. What we try looking to do is try to build a data pipeline whose latency is measured in minutes, at the minimum less than 30 minutes or less. And these data should be analytics ready. That means they are, excuse me, they are refined to a degree that anybody can readily consume these data. Okay. So the very first thing we do is build a data ingestion. We use Apache Flume as the backbone to ingest the data. If you look at our lower left, this is the site database. We call that term, this is our MoneyDB. All that money you transact on PayPal actually gets logged in this database. This is very, very mission critical. It needs to be up 99.999% of the time. We use very, very high-end hardware for that. So not to go ahead add any more load, we built a staging database. It's going to go as more like an operational data store. So that pull the delta happens in the database into this database. Then from this point on, we pull the data via Flume to our Hadoop endpoint. So if you see the dashed line in the middle, that represents data flowing in the internet. Because typically your production data center is separate or different from your analytics data centers where people do back-end analytics work. So we have to be able to have something that encrypts the data and send data via Flume across the internet. Once it lands in the analytical data center, we push it to our Hadoop clusters. We have two. One is for production, where SLA is guaranteed, or the other one is an R&D center that has a lot more storage, support a variety of use cases. So how does this site to Hadoop pipeline look like? We continue to stream this via Flume. That means data does not arrive every day or every few hours. Data arrives every few minutes. And this entire from site to Hadoop architecture, we have HA built into this. It's highly, highly resilient, redundant. So we start at Oracle layer. Oops. The Oracle, we use Oracle Grid. That means, and they go into a shared, highly reliable storage system. That means we can afford losing an Oracle node. And the system, the data source is still there. And the Flume pipeline, we have two pipelines. So if one goes down, the other one will continue to be available. then we'll dual write the data to 2 Hadoop cluster. So for whatever reason, if my production cluster goes down, or if I have to take it down to upgrade or do something, I can fail over to my R&D cluster to keep the pipeline going. And this whole system, end-to-end, we have monitored built in via Ganglia. And we're also looking to add a nodules alert such that when some threshold gets across, we can do something about it. All right. Some of the key learnings we have found is that if you are taking data out of your production data center, you need to be best friends with your IT folks and make sure that they give you a dedicated network topology that is different from the network that's serving incoming users, right? eBay, PayPal, we get millions of hits every few minutes. And you make sure when you move data, you better not interfere with that network topology. So having separate network topology is almost a given. Then you have sufficient WAN bandwidth. One of the key lessons we have learned is that if you don't plan carefully, you start your Hadoop cluster, but there's not sufficient bandwidth to pull data from the data source to your Hadoop cluster, and none of your data team can actually do meaningful work. And one other thing we actually just find is that you want to make sure there's enough least capacity across your data center, and that you want to have some kind of burst capability such that you have a need to be able to land some additional data there. You can burst into maybe some WAN providers who give you a temporary bandwidth boost. Okay. Landing data on Hadoop, right? These are raw data, right? We do a data quality check to make sure that the number of rows matches from the Oracle side to the Hive side. Then we create Hive partition. Every few minutes, a new Hive partition getting created for each of the Oracle tables. Then every day, obviously, you have many, many, many small partitions, per table. If you talk about lots and lots of tables, you're creating too many, small things that's not conducive for downstream analytics. So we have a daily compaction job that compacts all these small partitions into a daily partition. We have hcalog support out of the box such that folks who want to use MapReduce and Pig to process their data can go through the same API. One of the benefits is that we are taking these raw data to Hadoop, and front-end developer who are very familiar with the Oracle schema at the transaction layer can immediately jump onto Hadoop and do data work on this. Okay. So with that, we'll move on to data processing. Okay, now we've landed raw data on Hadoop. What do we do with it next? Okay. Raw data, we forklift these Oracle tables to Hadoop. Oracle, by definition, is a transactional system, so the schema is highly optimized to get your transactions to go through very fast. That raw data is not optimized for analytics. But what's worse is that these data are highly, highly encoded. There'll be a bitmap, bit streams with different flags. Each flag would represent a different logic meanings. If we just give that data to the end consumers, who all the downstream applications must, one, they have to implement decode logic on their own. So you're duplicating work. But the key thing is, if there's an Oracle schema change, that means somebody add a new flag or even change the meaning of a flag. You have to have all your downstream applications to be updated simultaneously. If you work in a big enterprise, you know that it's next to impossible to push every team to change the application at the same time. Just not going to happen. So we need to go ahead and convert the raw data into something called analytics-ready data. What we mean is that we would like to create some foundational ETL layer such that this serves as a simple abstraction against your raw data, so that raw data gets converted into something here all the downstream application can use. So graphically, you can think about this is that this foundational ETL layer sits on top of the data central, the data repository that holds all the raw data. Then all the upstream application will interact directly with the data set exposed by this. The goal, just make the raw data more digestible. Okay. So the very first thing we've done is expose everything via Hive, since it's a SQL-like interface, and developers and the business analysts all love to use Hive. So what we do is we leverage existing logic, the logic to decode Oracle schema that already exists within the firm, right? So no point to reinvent the wheel. We leverage the existing logic, then we pre-join some tables, pre-compute some of the matrix, because everybody will need this sort of thing. Example is, what is my current total payment volume from midnight till this point? How is these things break down by different geo regions, whether it's North America, APAC, or EMEA, right? Then every time we create, for this sort of thing, we add a new partition per Hive table. And obviously with Hive and HCatalog being part of the Hive, we support HCat integration out of box. So this table works very well for all the Oracle tables that are inserts only. That means I can incrementally just adding more data to my Hive partitions. But the problem is, Oracle being a relational database, it can be updated. But we cannot really easily make update with HDFS data. So how do we support data that's being heavily updated on the Oracle side? And sometimes you just have a need to really access a small slice of data. So me as a business user say, I would like to look at merchant A. And what is that merchant's data sales volume for the last 24 hours or last week? For a brute force Hive full table scan, that means you're scanning every single merchant data out of disk, throw away more than 99.9% of your data, just looking at that small slice. That is very inefficient. So these are the problems we have if you only expose your data set via Hive. Luckily, HBase comes to the rescue. So we have built another downstream pipeline from the initial set of Hive tables that setting the data through an HBase systems on the same Hadoop cluster. The idea is I have these very dynamic data changes coming from merchants, who are one of the key revenue contributor for PayPal business, or consumers, people who are using PayPal buying things on the web. The idea is we build this merchant or consumer data store that holds all the information related to a merchant and data, such that you can access this data very, very quickly. Right? The idea is that we expose this data set via some of the Hive tables. Hive is very simple, put and get APIs. It also gives us something very important called a point-in-time representation. I would like to see what is that customer's address and email a year ago versus 6 months ago versus a week ago. That is very important from a risk use cases. A lot of fraudsters, they open a PayPal account and sometimes they change their customer contact information very quickly and want to be able to capture this delta change in the data state throughout time. Okay. Everything being Hive, right? We have the benefit I can access a very small slice of data and with millisecond latencies. Right? And this end-to-end pipeline with the initial data ingestion and the Hive work, we're still trying to keep the whole end-to-end latency less than an hour. Okay. So once we have the raw data, not necessarily raw, but refined data in Hive and be able to support different use cases, then we continue to pre-aggregate additional commonly used matrix. For every single merchant, we produce a matrix like sales by time, geography, and how much of that traffic comes from web versus mobile. These are commonly used things that everybody who looks at PayPal sales data will want to know about it. Then the whole pipeline we built is through a pluggable architecture that it builds a set of interfaces such that if you want to generate a new matrix, it's very simple just to go to implement a couple of Java method. And this new matrix will just go to appear in your HBase cat. Okay, so next I'm going to talk about is graph. Now, you can access data through either HBase or through Hive. But PayPal data, by its very nature, they form a graph. So what can we do with that? So let's look at a very simple transaction. User 1 buys something from a merchant. Then user 2 buys something from the same merchant, and they send money among each other. So by definition, you have some notion called entity, which are a user account or a merchant account. These entity or nodes are linked together by the transactions. The idea is that if we view this data through a graph lens, are there new insights we can infer by mining the entity relationship? There are risk use cases that's give you something here like if user 1 is a very trusted 10-year PayPal users, we know we can trust the user. So whenever he makes a transaction, the system will let him through. If user 2 is a very new user, we know very little about this particular user. When he and she makes a transaction, what should our risk engine do? Can we aid our risk determination by the fact that user 1, user 2 have transaction with each other? Since we trust user 1, therefore I can trust user 2 a little more than a pure brand new user. So these are the use cases we're trying to support through a graph-oriented way to look at our data. Okay. For that, we use another open source graph database called Titan. The thing we like about Titan is not just that it's open source and scalable, but it sits on top of Apache HBase. That means we do not have to build a brand new cluster. We can just go ahead use our Hadoop clusters, which with out-of-box HBase support. We don't have to set up a new cluster, copy data into a new system. This thing can exist on an existing Hadoop infrastructure. And it is highly, highly scalable. It can scale to billions of nodes and edges. So with Titan, this thing here, we extending our pipeline a little further. Initially, after we ingest data, we put this into Hive with RC file. Then we have a pipeline pushing this in Apache HBase. Then we periodically pull things out of using a graph batch. Or you can also use Apache Giraffe as another processing layer to do additional graph processing. Then you send data to your Titan database. And the Titan supports a graph query language using Gremlin. So they can start to go ahead and query the database to say that, given this user or given this account, what are the other users or nodes that's related to this? And you can very efficiently traverse the graph to find information what you need. Another byfact is that Titan comes with Elasticsearch as a piece that gets installed. Then you can turn this, start to index all the data you put in your HBase or /Titan graph database, and open up a search service to the user. So I can start to type in maybe a username or a merchant name, and it will get related user account ID, which helps me to use that information to do additional search. Okay. So we've done all this processing work on Hadoop. And we need to go ahead and make that information available for end users to consume. So we built a third piece called the data service. The idea is to offer these data insight as a service for both internal users that's building internal applications or pushing this to PayPal.com, where some of the work we've done on Hadoop start to power the user experience on the external-facing website. Okay. All right. So this section, we're going to focus on how do we deliver insights to end users or applications that are not on Hadoop. How do we pull data out of Hadoop? Very traditional, right? You do a batch load out of Hadoop, right? And most of you, if you're doing Hadoop, this is something you're pretty familiar with, right? You do an HDFS get, you pull something out of Hadoop, and you land this on a disk somewhere outside HDFS. Then use a tool to load this into your application data store. Next, another approach we do is exposing the data inside as a service, directly serving data out of Hadoop. Sometimes, you probably use BI tools. Before Hadoop, you have Oracle, Teradata, you have tools like Tableau, MicroStrategy. People are already familiar using BI tools, getting insights from your data store. So this time I'm going to talk about what are the additional BI tools we use. There was a direct Hadoop integration with that. This one here is our internal applications where we use Oracle. So we use an ETL tool, and the ETL tool offers you a couple of things, right? They already have connectors built into that pull data out of Hadoop and push data into your data store. So we do not need to develop additional connectors. That's something here we would rather outsource to a vendor. And these tools are going to offer parallel data loading and also some of the reliability features. So that's something here we decide to use an external vendor's tool versus building something internally. Okay. Next, we're looking at into a notion that how can we use all the insights we generate on Hadoop, offer the insight as a data as a service that can power various things that's running within PayPal. Luckily, that we have HBase that contains a lot of base. On every HBase's region server, there's a thrift store servers. Thrift effectively, it's a data serialization technology that if you talk thrift, you can immediately pull data, talk to this one, pull data out of HBase. And we decided to add a RESTful web services because that's a de facto standard within the company. And every single business logic or some of the, and within PayPal, effectively the standard is using a RESTful interface. And all we did is adding a protocol converters such that people can directly consume the REST service and pull data or pull insights out of the HBase system. Also, we also use some of the vendor tools. So one of the vendor we're working on is called Platfora. Platfora itself offers some direct Hadoop integration out of the box. We felt it's going to meet our use cases. At the very low layer, you can go through GUI. You can use a Platfora to generate MapReduce code and does your data processing on Hadoop. Once this data is pre-computed, pre-aggregated, and you can pull this one into a middle caching tier. This caching tier is distributed. So in a way, it's somewhat similar to a lot of traditional BI tools like MicroStrategy or Cognos. This particular in-memory caching tier not only holds the data, but also exposes the data through the platforms building the GUI tools that you can build very simple, dashboards, pie charts, very simple. But also offers a RESTful web services. And this RESTful web services we can expose to the entire enterprise such that other applications can connect to this platform and pull data insights out of it directly. Okay. So overall, putting all this together, how does this look like? At the very bottom, we have Data Central that pulls data from transactional data sources, logs, third-party data. These are just raw data landing on Hadoop. And we build a foundational ETL to transform this data into something you can consume directly. On top of it, we start to build what I call big data services, whether it's a graph service allow you to do graph analytics, or search service, nothing more than standard Apache, Lucene kind of Solr or Elastic sort of thing to be able to say that I want to go ahead and index all my text data and be able to return a piece of data to me very quickly. And some of our consumer and the merchant data stores exposed as a service that can be consumed by applications inside Hadoop and outside Hadoop. We built out this platform to be able to power various use cases within, right? Merchant insights, very simple things. We're helping merchants to understand how their sales, standard your sales analytics that runs on top of Hadoop, looking at merchants' data across time, geography, or custom access channels, web, tablet, or smartphones. We also use this thing to power consumer credits. PayPal has a business unit that offers credit on the spot if you're going to buy something called a BML, and we want to be able to use some of the data to be able to say that how creditworthy a new user it is. Should I offer him a credit, and how much should I offer that users? Right. Risk mitigation is a major thing here, right? With so much money flowing through the PayPal network, risk is a major undertaking, investment PayPal's making, that we use some of these capabilities to power various risk use cases. And there are other use cases we're going to put together, right? And this is the commerce data pipeline we built, and also some of the pieces that we're in the process of building to power different use cases. Okay. Before I end, I'm going to talk about our experience. How do we go from Hadoop 1.0 to 2.0? When we start this project, we are still on Hadoop 1.0, the standard MapReduce work, right? We already have 2 production clusters running a vendor's 1.0 distribution. We already have production data. So how do we migrate this to a 2.0 thing while still pushing out the new capabilities? This is analogous to how do you keep the car going at 120 miles an hour and start to change the tire or change the engine. So we start with this is that we create a 3rd production cluster that runs on the Hadoop 2.0 distribution. Then we give all the production users, all the teams who's got production jobs, plenty of time to certify their production workload, their code on Hadoop. And what we discovered is that as long as you have Java code and MapReduce or Pig and Hive UDF, and you recompile your code, and pretty much works out of the box. There are some minor incompatibility, but most of these incompatibilities are minor that, small number amount of code change took care of most of these issues. Then we give a user a pretty long window. So both the Hadoop 1.0 and 2.0 production cluster are in production in parallel. And we encourage the user and we incentivize them to move over to the new cluster, but give them enough time because every single production job has a different business stakeholders with a different timelines. Having both clusters going at the same time make this migration very, very easy. And the last thing is we try to stick with HCatalog, that we do not want users to directly access the data. For example, if people start to go directly to access the RC file, that makes it very, very expensive or almost impossible to convert this from RC file to ORC file in Hive 12 or Hive 13. We'd like to create this data abstraction on top of it such that in the future, right, if we find that Parquet is the right data storage platform to use, we can start to swap out the storage format without impacting end user, as the users just continue to access data via high-level HCatalog APIs. Some of the future work, right? Disk is getting cheap. Disk is very cheap, right? And even SSD is getting cheap, right? Memory is getting plentiful, right? And I remember more than 4 or 5 years ago, right? You got a box with about 32, if you're lucky, 60 gigabyte of memory. But nowadays, if you want to buy a Hadoop data node, you start with 128, right? Within a year or two, you go to 256. Memory is becoming your new disk. So we're looking to really leverage in-memory technology to be able to push our pipeline from, to be, disk/memory-based to memory-based only. So we felt Spark Shark is a very promising field for us to move some of the pipeline. In fact, we have a prototype actually working, implementing an end-to-end, ETL logic Spark Shark, and they work reasonably well. We didn't see a major problem with this. And if you go to an Apache Hadoop 2.4, some HDFs start to support in-memory databases, and that's something here we're looking forward to taking advantage of. Some of the streaming processing work, right? If you push everything to Hadoop, there's going to be latency built in, especially you have to move data from your production data center to your analytics data center. So we're looking to actually do some of the streaming processing in our production data center using a combination of Kafka and Store. So it's exactly 2 seconds left, but I can stay a little behind to answer any questions. Okay. Thank you.